row. So for any epsilon positive, we find a row. The row is determined by, we use epsilon to determine a delta, and then we use this delta and the limit 0 condition here to determine this row. So if the norm of h is less than rho, then the norm of bh plus eta h is less than delta. But once the norm of k is less than delta, lambda k, the norm of lambda k will less than this will have this inequality. Therefore, combine this together, we see that if the norm of h is less than the rho, then the norm of bh plus eta h is less than bh plus eta h will less than delta. Therefore, by this inequality, we will see that lambda, because the norm of bh plus eta h is less than delta, this bh plus eta h can be the k here. So lambda bh plus eta h will not greater than epsilon, the norm of b plus 1, and the norm of bh plus eta h. bh plus eta h. bh plus eta h bh plus eta h will not greater than b plus 1, will not greater than the norm of b and the norm of h plus the norm of h, because we previously assumed that without loss of generality, we assume that the norm of eta h is less than h. Okay, so what's this? This we can take the norm of h out, and we obtain the norm of b plus 1, and that can be cancelled here. So eventually this become epsilon h. No way to write. Okay, I write it. Okay. This is epsilon norm of h. So in conclusion, we prove that I have to write next page. We prove that any epsilon positive, there exists rho positive. If the norm of h is less than rho, then lambda bh plus eta h is not greater than epsilon norm of h, or lambda bh plus eta h divided by the norm of h is not greater than epsilon. This means the limit h goes to 0, lambda bh plus eta h divided by the h is 0. This proves the limit we want here. Previously, we have declared that once we prove this limit, our theorem will be valid. Now the limit is proved, so the proof of this theorem is complete. Okay. Now we have proved the chain rule. In the chain rule, the maps f and g have to be differentiable. This condition is slightly strong, but it ensures the differentiability of the composition. If we want to ensure that the partial derivative of the composition exists, we can weaken the assumption. We only require f to be differentiable. We don't need g to be differentiable. This is interesting. Okay, this is a corollary of the chain rule. So, if DIGA exists for some I, and f is differentiable at B is FA, GA. Then the composition. For the composition, composition is a map from BRA to RL as before. The partial derivative exists. And the partial derivative at the point A, sorry, this is A. The partial derivative at the point A, partial derivative at the point A exists. And this partial derivative at the point A is f point B. The partial derivative of G at A. So we don't need to assume that G is differentiable at A. Okay, this is interesting. But our theorem requires the differentiability of both F and G. But now we only have the differentiability of F. G is not necessarily differentiable. How to apply the theorem? Before review the idea of this, let's have a look on this condition. Here, BRA is a ball in Rn. Map in U is a ball in Rm, open set in Rm, and our F is still vector valued. Okay, so this is the F composition of F and G. So the proof. Since the partial derivative exists, this map we denote it by phi minus RR to Rm. Phi t is GA plus TEI. EI is the i's basic vector 0, 0, 0, 1 in the I slope and the other 0. Okay. This map is differentiable. At t equal to 0. Okay. Partial derivative is the by definition is the derivative of this single variable function phi at the origin at 0. Okay, remember this is the definition of partial derivative. So this is differentiable. So although G is not differentiable, we have this phi which is differentiable. So we apply the chain law to the composition of F and phi. We draw a picture. Here is the real line, and this is the origin, and this is minus R. So this map is our phi. This is our phi. Phi is the composition of G and this map. This map T to A plus TEI. So this map composed with G is our phi. Okay. So by the chain law, our since phi is differentiable at t equal to 0, by chain rule, the map t to the f g a plus tei. This is the composition of f and phi. At the value t. This map is differentiable at t equal to 0. And the derivative, this map we denote by psi. Okay? And the derivative is the derivative of f at the point B, and the derivative of phi at 0. But the derivative of phi at 0 is nothing but the partial derivative of g at the point A. On the other hand, by the definition of partial derivative, the left hand side, psi point 0, is the derivative of f, the composition at A. You will observe this, why this is true? Because our psi t is f composed with g at the point A plus tei. Okay, so this means that the derivative of the single variable function psi is the partial derivative of the composition f and g at the point A with respect to xi. So this proves our result. This proved this result. So the corollary is proved. This is very clever. Okay, so it is at the first glance, since g is not differentiable, it is unexpected that we can use the chain rule to prove this corollary. Okay. Now, we consider another important problem. So, f defined BRA to Rm is differentiable at A. Okay, and we define this G to be map T to A plus T H, given H, H in Rn. Here H is a vector in Rn. Okay, then obviously this is differentiable. This is differentiable. Okay, very simple linear function is differentiable. So we apply the chain rule to this map minus epsilon. This is a map to BRA, maybe minus R. This map is our G. When T is 0, that is A. The absolute value is not greater than R. Then A plus TH will lies in this ball. So this is our G. And our F map in Rn. So we consider this map. So by the chain rule, this map is the composition. The composition, the derivative of the composition at t equal to 0. What's this? This is f a plus th, right? gt is a plus th. Therefore, the composition at t is f a plus th. So the derivative of the composition is this. By the chain rule, this is the derivative of f at a, and the derivative of g at 0. G at 0 is h, because h has a very simple form. So the derivative of g at 0 is easy to compute. This is h. So this is the f prime a h. So this is a very useful formula to compute the derivative acting on a vector h. That is, the derivative of f at a acting on the vector h is the directional derivative of f at a in the direction of h. This can be read in this way. Okay. Of course, here I talk about directional derivative. Previously, we studied directional derivative for real-valued functions. But now our f is a vector-valued function. So what's the derivative? What's the directional derivative of f at a in the direction of h? It is easy. F is a vector-valued function. It has m components. The components of f are real-valued functions. So it is natural and no surprise that the directional derivative of this vector-valued function is a vector whose components are the directional derivative of the components functions. Okay, so you can consider this as the definition of directional derivatives for vector-valued functions. Okay. So this is the chain rule and the related topics. Okay.